share my screen now. Please let me know if you can see the screen. We are now on chemical energy.
Yes, Miss Sarah.
Okay, so let me just decrease the size. It's too big. Okay, I think this is it. Now, just a short review. So last meeting, we have discussed. So we started with the concept of energy. Then we discussed work and heat as a form of energy. And after which we ended with the topic on mechanical energy, which constitutes the kinetic energy and the potential energy. So for this afternoon, since we have 3 hours of class, I will try to finish the entire module, but we will have breaks in between so that it will not really be mentally draining for everybody. Okay, so we are now on chemical energy. Okay, I need to admit somebody. Now, when we speak of chemical energy, so this is the energy that is released during a chemical reaction or a change in the composition of a substance. So when a substance changes identity, changes in characteristics, then it follows that there's a corresponding change in its chemical energy. So energy is required to bond atoms together, and energy is released when these bonds are broken. Now, speaking of bonds class, so a particular substance, in order for it to form atoms of different substances, actually bond with each other. Now, when we have to conduct a particular experiment in such a manner that a particular chemical is to be reacted with another, they cannot form new bonds with a different substance unless the existing bonds are broken. So the existing bonds that needs to be broken need what we call energy for these bonds to be broken. So existing bonds have to be broken so that new bonds will be formed. And that's in the case of a chemical reaction. So you could see in here that there is this bond existing between these two atoms. These bonds have to be broken. That way, these atoms here, which are red, can bond with another atom, let's say, for example, which is different, or let's say a different color, which is blue. So no bonding will occur between substances unless the existing bonds will or should be broken. Now, chemical energy, for that matter, can be viewed as that energy that is stored in some kind of chemical substance. And the energy is released when these substances mix together to cause a chemical reaction. So there is needed energy for the bonds that will be broken. And there is also, take note of this term here, release of energy when bonds are broken. Now, during photosynthesis, we know this since elementary. The first time I can remember that photosynthesis was discussed to me was when I was in my elementary. So this is the process in which plants make food or produce the fruits that we are also consuming as food. So the plants in the process of photosynthesis converts light energy coming from the sun into chemical energy. Chemical energy that is stored in its fruits. Okay, so you have the process of photosynthesis here. Now, on the other hand, when we speak of electromechanical or rather electromagnetic energy, since we're done with mechanical energy already, this is a form of energy that is reflected or emitted from objects in the form of electrical and magnetic waves that can travel through space. So a form of energy that an object may emit or that an object may reflect is a form of electrical and magnetic wave. So as such, it's called electromagnetic energy. And take note of this class, it can travel through space. It can even travel through vacuum. Anybody here who can tell me a specific type of transfer or energy that is transferred through vacuum? An energy that can be transferred to an empty space or through an empty space, which is vacuum. Anybody here who knows that particular type of energy or a transfer of energy? It can travel through space or even something that is really nothing or a thing that has nothing on it, which is vacuum. What is that form of transfer in which it's traveling through vacuum?
Electromagnetic.
Electromagnetic, or what's the single term that we can associate it with? Anyone? A kind,
Radiation.
again?
Radiation.
Very good, very good. So that's the term, radiation. So it's a form of transfer of energy, specifically heat energy, through nothing, through an empty space, which is vacuum. By the way, it's the only thing that can travel through vacuum. And it's also in the form of electromagnetic waves. Okay, so examples of electromagnetic energy include, so we have power lines. Of course, there are power lines where our electricity is being transmitted to from a certain source through our homes and to the industry facilities, even to schools and any other facilities for that matter. So power lines. Another one is electric motors that are driven by electromagnetic energy. And also we have what we call light. Light as a form of energy is transferred or emitted in the form of electromagnetic waves. So that's electromagnetic energy. Now we also have what we call nuclear energy. Some from the term nucleus. So where can we find the nucleus? So it's that what? The nucleus is what? Anyone? The nucleus is the what?
The center of a cell.
The center of an atom. Okay, it's okay, Hans. So the nucleus is the center of the atom, the central part of the atom. And once an atom is broken down, or shall I say disintegrated, we form what we call nuclear energy. Or there is tremendous energy that can be produced once an atom is split into two. So nuclear energy is the energy released during nuclear fission or fusion. So fusion coming together, fission breaking down into different forms or parts of nuclear energy. The fission happens when the nucleus splits and nuclear energy is released in the form of light and energy. Nuclear energy is also released during fusion. That is when nuclei collide at high speeds and form as one atom or form as one atom which has the two nuclei joined together. So as such, it's referred to as fusion. But when there is division or fragmentation, then we refer to as fission. So the sun's energy is produced from nuclear fusion, reaction in which hydrogen nuclei fuse to form helium nuclei. So the hydrogen forming a helium nuclei. Hydrogen is only one, okay? Now, when it fused to form one particular atom, which is the helium nuclei, the process is nuclear fusion. Fusion meaning the fusing of two atoms. Now, let's go to the law of conservation of energy. So we know this is very elementary and fundamental. Energy cannot be created nor destroyed. It is simply transformed from one form into another. So you don't create energy, you don't destroy it, but rather you just simply transform it from one form into another. So in 1905, the very famous Albert Einstein proposed that mass and energy can be converted into each other. He showed that if matter is destroyed, energy is created. Then if energy is destroyed, mass in the process is created. Now you have here a picture. So since we have the law of conservation of energy, which states that one energy can be transformed into another, so the classic example here is the throwing of a ball upwards, which follows this particular path, a curved path. Okay, so the law of conservation of energy can be illustrated by this bouncing ball or a ball that is thrown upward. As the ball bounces up, it gains potential energy by virtue of its elevation from a certain base point, which is the ground. Okay, so we have the h as the elevation, the mass of the ball, and the gravitational constant g all being multiplied to give us the potential energy of the ball, which is said to be highest at this particular point here. Okay, highest potential energy. So as the ball falls from its highest potential point, potential energy is converted to kinetic energy. So the potential energy of the ball at this point is now being converted to kinetic energy. Just before the ball falls to the ground and stops, all of the potential energy have been converted into kinetic energy, and the ball gains its maximum velocity just before it hits the ground. Why is that? Because you will learn in physics that once the ball is on the ground already, it's said to be at rest, or it will stop because there's the ground to stop its movement going downward continuously. So then at that point, the velocity of the ball will be now not maximum but rather zero. So the maximum velocity of the ball as it converts its potential energy at this highest point to kinetic energy is just before it hits the ground. If you may notice also, as the ball continues to bounce, the height that it reaches diminishes. So let's say, for example, in the case of a bouncing ball, as the ball tries to bounce from one point to another, its height in reference to the ground will continuously diminish until such time that your ball will not anymore bounce, as in it will simply roll. Okay? So such happens because as the ball falls to the ground, sound is created. And so some of the mechanical energy have been converted into sound energy. So potential to kinetic, which is actually both forms of mechanical energy, to sound energy. So the reason why, so if you would be asked why the ball will not keep its original height in bouncing back and forth to the ground when thrown, it's because some of its mechanical energy is converted already to sound energy. So that's just a process of how energy gets transformed from one form to another. So ini siya very classic example ni siya nga always ginasite in terms of the conversion of energy from one form into another. So another examples or examples that are stated here also in your notes would be the sun's energy through solar cells can be converted directly to electricity. So in the case of solar panels that stores the energy from the sun, and then during at night when there's no sun anymore, this stored energy is used to light up our houses, the offices, or the industrial facility for that matter, for those who are using solar panels. Now, we also have green plants convert the sun's energy into starches and sugar. So we know plants produce food or produce the food that we eat. And in the food that we eat, we have there the carbohydrates, the sugars. So it's actually the radiant energy of the sun being used by the plants to form the fruits that we are eating. So that's also a form of conversion of radiant energy of the sun to chemical energy that the consumers are eating. So we are consumers. The animals are also the consumers. So we are taking in chemical energy from the fruits of the plants, or even from the vegetables that we are eating. Okay. In the case of the automobile engine, fuel is burned to convert chemical energy from the fuel into heat energy, and then the heat energy is then changed into mechanical energy. The burning of the fuel inside the engines of our automobiles produces heat, and in the process this heat energy is used in turning the gears in our automobile. That is why the wheels of the car keeps on rolling, because of the conversion of heat energy into mechanical energy. So these are just observable common day-to-day phenomena where transformation of energy can be observed. So maybe there are still things that are not included here, and I'm certain of that there's still a lot, an infinite number of examples in the conversion of energy from one form into another. So we're done with energy, heat, work, mechanical energy, even electromagnetic energy and nuclear energy, together with chemical energy here. So we go now to heat. Heat. So you will study this in details later on when you go to thermodynamics. It's the study of how heat is being transferred from one object to another. And heat is the transfer of thermal energy from one object to another because of a temperature difference. So take note of the term here, temperature difference. So heat will never transfer unless and when there is a temperature difference existing between the objects in which it is to transfer to or from. So, hindi pwede mag-transfer ang heat kung ang temperatures ng duha ka objects equal. So, there has to be a temperature difference. Now, heat always flows spontaneously. So, it's something that is spontaneous, something that does not require any outside or external disturbance for it to occur. So, it happens from a hot object to a cold object, or from a high temperature material to a low temperature material. Otherwise, there will not be any transfer. So it must be noted that heat is not a form of matter, but rather heat is a form of energy, and it requires what we call temperature difference. Okay, temperature and heat are actually associated with one another, but they are not the same. Associated lang, but not the same. Temperature is a measure of the average kinetic energy of all the particles that a substance or matter has. And temperature tells us whether something is hot or cold. Now, in a way, it tells you also of the amount of energy that is stored in a particular material. So this heat is or can be expressed using the following units, and some of you may have encountered them already in your high school physics. So calorie is a unit for heat, and it's the amount of heat required to raise the temperature of 1 gram of water by 1 Celsius degree. A calorie, a unit calorie is actually associated most of the time with water. But when you go to your thermodynamics later, you will encounter this unit calorie often. Okay? Amount of heat. So what is that amount of heat that will raise the temperature of 1 gram of water by 1 degree Celsius? That's your calorie. Now, in the English unit, we use the British thermal unit for the unit for heat, British thermal unit. And this is the amount of heat required to raise the temperature of, so we're still using water, 1 pound of water by 1 degree Fahrenheit. So this one is just the English unit, and this one is actually it's not the SI unit, but another unit for expressing heat. The SI unit for heat is actually the joule. Okay, the joule shows the relationship between energy in the form of work and energy in the form of heat, known as mechanical equivalent of heat. The joule actually unit is Newton meter. So if it's broken down into basic units, it's Newton meter, and it can be used for both heat and work as a unit. Okay, so you have here different conversion factors of the units of heat here that is stated on top. So a kilocalorie, from the prefix kilo, has 1,000 calories. And 1 BTU is equivalent to 252 calories, also equivalent to 778 foot-pound force. And your calorie is equivalent to 4 0.186 joule. Okay, so this is for heat. Now, as to the kinds of heat, you will again actually encounter this in thermodynamics. We have what we call sensible heat or what we call latent heat. So sensible and latent heat. Now, sensible heat is the amount of heat required to change the temperature of the substance without changing its phase. So take, for example, heating water at 25 degrees Celsius to 78 degrees Celsius at normal atmospheric condition, or simply room temperature, room condition. Only the temperature of water changed in this particular increase in temperature, but it is still in the liquid phase. Or if we will simplify the definition of sensible heat class, it's just the heat required to change the temperature of the object. Just simply change its temperature. It could be from a higher temperature to a lower temperature or lower temperature to a higher temperature. Simply changing its temperature. So associated with a difference in temperature or a change in temperature. But there is no change in phase. I think it's already forthcoming on what we mean with sensible heat. So sensible heat, on the other hand, already, or rather latent heat. Latent heat, on the other hand, already takes into account that you will change water, let's say, for example, from the liquid phase to the gas phase, or from the gas phase to the liquid phase, or from the solid phase to the liquid phase. We're still talking of water. In these changes of phases of your water from solid to liquid, liquid to gas to liquid, there will be what we call latent heat that is being required. So what is this latent heat? It is the amount of heat required to change the phase of the substance without changing its temperature. Under normal atmospheric conditions, water freezes and ice melts at 0 degrees Celsius. So latent heat is involved when ice melts. So during melting, only the phase changes from ice to liquid water, but the temperature remains at 0 degrees Celsius. So let me explain this, class. When your ice, for example, that is, let's say, for example, let's say your ref, in the current smart ref now available in the market, your ref is set at, let's say, for example, negative 19 degrees Celsius. Of course, at that particular temperature, the water that you place inside your freezers will turn solid. Okay, so it's already in solid form, but its temperature is negative 19 degrees Celsius. Before you can melt that solid ice in 19 degrees, negative 19 degrees Celsius, before you can melt it, you need to increase first its temperature to 0 degrees Celsius. So from negative 19 to 0 degrees Celsius, you have what we call a sensible heat. Why sensible heat? You just change the temperature of ice from negative 19 to 0, but you did not change the ice from solid to liquid. Now, once your ice is already in the 0 degrees Celsius temperature, it's now ready to be converted to a different phase. So from solid, let's say, to liquid. So then you will be needing another form of energy to do that. And that particular form of energy is latent energy or latent heat. Why? Because from solid 0 degrees Celsius, you will turn your solid ice into liquid water, which is still, class, which is still 0 degrees Celsius. So a change of phase, but no change in temperature. Now, if you want to increase the temperature of that melted ice, which is now liquid water, for example, to 20 degrees Celsius, that again will require another what we call sensible heat. A change in temperature from 0 to 20, but there is no change of phase. Now, you need to increase the temperature of the 20 degrees Celsius liquid water to 100 degrees Celsius. That way, now you will be able to convert your liquid water to water vapor. But listen, from 20 to 100 degrees Celsius, that is still sensible heat because you change the temperature from 20 to 100 degrees Celsius. In order for your liquid water to form into water vapor, your 100 degrees Celsius liquid water needs latent heat again to convert your liquid water at 100 degrees Celsius to water vapor at 100 degrees Celsius. So in latent energy or in latent heat, there is no change in temperature, only a change in phase. Whereas in sensible heat, there is a change in temperature, but no change in phase. So you should be able to distinguish these two, sensible and latent heat, because you will meet them again in thermodynamics. So I have here example of sensible heat. Okay, only this one for now. Now, sensible heat may be calculated using the following formula. So you have Q equal to the mass of the material, the specific heat of the material, or we call it specific heat capacity, and the corresponding change in temperature. Why there's a delta T? Because in the first place, sensible heat is that amount of energy associated with a change in temperature, but no change in phase. So specific heat, the Cp that you see here, is the ratio of the heat transferred to the corresponding rise in its temperature. And actually, class Cp is a characteristic of any material. So materials vary in their specific heat capacity. The higher the heat capacity of the material, the higher the amount of energy that can be stored in that particular material. Again, I will repeat, the higher the specific heat capacity of the material, the higher is the amount of energy that can be stored in that particular material. Why is that? Because you could see this in the formula. I increase Cp, the Q will also be increased because the two are directly proportional. So different substances have different capacities for storing heat. So this is already what I've mentioned. Likewise, different materials require different quantities of heat to raise the temperature through a specified number of degrees. So dalain-lain man kay tungod nga ang CP sang materials different. The value of the specific heat varies for different materials, as different materials also absorb energy in different ways. So higher Cp, higher rate of absorption. These are just but the common specific heats of different substances. There are still substances that are not written here. So in the case of aluminum, this is the specific heat of aluminum, 900. In the case of ice, the specific heat is 2,100. In the case of hydrogen gas, look at it. Its specific heat is 14,000. Okay? And then for the, what is the highest here? I think it's the hydrogen, because the others, for this group, ethanol has only 2,400 and nitrogen has only 4,186. Not that high compared to hydrogen in terms of their, specific heat. Okay? So the specific heat is very important when you are accounting for sensible heat. Heat associated with the change in temperature of a material or of an object. In the case of water, class, in the case of water, let me just go up. This is the CPs of water. So these are the CPs of water. Notice that they are not the same. When water is solid, the CP is 0.5. When water is liquid, it's 1. When it's gas or vapor, it's 0.498. So calorie per gram degree Celsius. If it's in joule, you also see it here. So 2.093. Then we also have 4.186. And we also have 2.085. Okay? This is in terms of the CP of water. These are the CP of the substances, common substances. Now, let me go to the sample problem here on sensible heat. Heat it is required to raise the temperature of a material without changing its phase. Okay, how much heat is absorbed by 15 grams of water if its temperature changes? So let me just annotate, class. This is changes, class. So if its temperature changes from 15 degrees Celsius to 60 degrees Celsius. So from the problem, you can pick out the given information. So you have the mass of water, its initial temperature, which is 15 degrees Celsius, and its final temperature, which is 60 degrees Celsius. Actually, class, there's no need for you to convert the temperatures here in Celsius to Kelvin because anyway, you are taking the temperature difference. So whatever you will add to this value here, it will anyway be 0, turn to 0 because you will also add it here when you take the difference. So there's no need for you to actually convert. But nonetheless, the equivalent of the Celsius temperatures here are this one in Kelvin. So from the table for water, liquid water that is, let me just close this one. Liquid water has a CP of 1.0 calorie per gram degree Celsius. And 1 calorie per gram degree Celsius is this one, 4.186 joules. So you will notice that in here, the unit that was used is joule. So CP for liquid water is 4186 joule per kilogram Kelvin. And this is your temperature difference. So the Kelvin temperature minus another Kelvin temperature, or you may do so getting the difference of the original Celsius temperature. The answer would be actually the same, which is 45.5 degrees Celsius or degree Kelvin, because we're talking of temperature difference here. So note delta T in Kelvin is also delta T in centigrade in Celsius, okay, or degree Celsius. So now what we have here is Q being equal to mCp delta T. This one is not anymore included, class. Na double type lang siya. So this one is not anymore to be written. So in this case, you have the mass of water, which is 0.015 kilograms. Then the CP of water, which is 4186 joule per kilogram Kelvin, and the delta T. So it's just actually a substitution to the formula of Q being equal to mCp delta T. Oh, here it is. So the mCp delta T formula. So you just substitute. The answer would be Q equal to 2856.945 joule. So this is the amount of heat absorbed by this 15 grams of water when its temperature was increased by 45.5 degrees Celsius. So this is how much is the increase in the temperature from this value of 15 degrees Celsius to 60.5 degrees Celsius. Okay? This is sensible heat. Okay, sensible heat. Now we go to latent heat. But before we go to that, let me just first clear what I have written here. So we go to latent heat. Okay, now latent heat may be calculated using the formula M times the H. Oh, where are you going to get the H, miss? The H is the difference in the enthalpy of the object, or we call it the latent heat. of the object. So Q is the heat, M is the mass, and H is the latent heat. Now, we will be using again water, class, water. So in the case of water, when it turns into liquid, so solid to liquid, this is its heat of fusion. When liquid turns to solid, this is its heat of solidification. So this is heat of, wait class, this is heat of fusion. Yeah, correct. And this is heat of solidification. For water, when it turns to liquid from solid, or vice versa, from liquid to solid. If water turns to gas from liquid, we call it evaporation. And your enthalpy change for that is 540 calories per gram. Whereas if gas, water gas or water vapor is turned into liquid in the process of condensation, this is its corresponding heat of condensation. Now, what about its direct from solid to gas in the case of the process of sublimation? So sublimation is a process wherein there's a change of phase from solid direct to gas. In the case of water, the heat of sublimation is the heat of fusion and the heat of vaporization, meaning the heat that is required to turn it to liquid and then the heat that is required to turn it to gas once it's already liquid. So you only take the sum of the two. The opposite of sublimation is like from gas, you turn it back to solid, and that's what we call deposition. Gas to solid, that's deposition. So we have it as the sum of the heat of solidification and the heat of condensation. So in the case of deposition, you will have an H value which is negative, just like heat of condensation and heat of solidification. In the case of sublimation, it's the same with the heat of fusion and the heat of vaporization, which are also positive. So positive 80, positive 540. We take the sum of the two, that would be positive 620 in the case of the heat of sublimation of water. That is, from the solid water, it will turn to gas directly. Now, I will have to ask you a question. Why do you think that for the solidification and the condensation, anyway, I will not ask about this anymore because anyway, that's copied from here. Why do you think is the sign of the heat, the values of the latent heat is negative? Solidification is negative 80. Condensation is negative 540. Why is these two negative, whereas ang fusion kag ang evaporation positive? Anyone here in the class who can tell me why nga negative ang solidification kag negative ang condensation nga heat transferred? So the exothermic, Harvey. Yes, is this Harvey?
Hi, Kieran, Miss.
Oh, sorry. Okay, I'm minimizing the gallery. So yes, Archer.
If mag-absorb energy, Miss, mag-positive enthalpy. And if mag-release energy, Miss, mag-negative enthalpy.
Very good. So the same thing with what I think Harvey placed here on the chat box. So if the process is endothermic, you're needing energy for it to happen. In the case of fusion, you will have it positive. You need energy for solid. You need energy for solid water to be converted to liquid. That would be in the case of the 80 calorie per gram here. It's needed. So it's something like the system needs that energy. Okay, absorption of energy. But on the other hand, the opposite, when liquid has to be turned to solid, there has to be release of energy. It's exothermic, or it's just like there is a release of energy, so that would be negative. So thank you for the two gentlemen there. So if it's absorption of energy, endothermic, it's positive. When it is release of energy or exothermic, that would be negative. This one, a direct change from solid to gas, is actually just copied from the previous two on top, because the energy that you'll be needing, it will be just the sum of the two that is outlined on top. Okay, so negative and positive signs for the energy released and for the energy absorbed. Now, you will be performing this particular laboratory experiment class. I don't know what's the order in which you're going to do your experiments in the laboratory virtually, that is this time. But one of your experiments has something to do with calorimetry. Calorimetry is when we take into account the amount of energies that is being absorbed or released by an object. So calorimetry is the term. So the law of heat exchange is associated with this release and absorption of energy in the form of heat. And in calorimetry, it's a fundamental concept in calorimetry that the heat released by one substance is the same heat release absorbed by another if these two substances are the only substances that are present in a particular environment. So meaning, one cannot release unless something will receive that released energy. So whatever is released, that same energy will be absorbed by another. That way, there will be no net energy increase in the environment. You see this zero here? So there should be no net energy increase in the environment. Otherwise, we'll be violating the law of thermodynamics. So the law of heat exchange is saying that one energy released by a substance is being absorbed by another. Or it could be class also if your system is not totally insulated. An energy released by one substance can be absorbed by another and some will be lost in the environment. But still, the total amount of energy that interacts in that same environment has to be equal to zero. So there should be no net sum of energy that is being formed in a particular environment. So it should be equal to zero. You have here the illustration in the case of the coffee. Okay, so if you have a hot coffee, the amount of energy that is being released by your hot coffee in a mug to the environment for it to cool down is the same amount of energy that your environment receives. Okay, and vice versa. Okay, if your environment, for example, if you have a furnace at home, let's say in those that are living in the western part of the globe, if they have their furnace to heat them up during winter, the amount of energy that is being released by the furnace in the form of heat is the same energy that the entire household is also receiving. That way, it would be enough for the entire household to be heated up during the, let's say, the cold season or the winter season, unless otherwise they will all be frozen alive in that particular environment. So it's the same thing. So one releases, another one accepts or absorbs that particular amount of energy. Or in symbol, that interaction could be written in this very simple manner. Q lost is plus Q gain should be equal to zero. The two have the same magnitude, they only differ in the sign. So Q gained is positive, whereas Q lost will be negative. Since they are of the same magnitude, thus the sum of the two will be equal to zero. So in the case of the coffee cup, we call it coffee cup calorimeter, that you will be seeing later on in your experiment. So there is an object that is placed inside the coffee cup, styro cup. Actually, this is a styro cup, and then there's also water inside. If the object that is placed inside the calorimeter coffee cup is hot, it will release its energy on the water inside the calorimeter cup. So on the assumption that no energy inside the cup will be lost in the environment where the styrofoam cup is placed, then whatever is the heat energy released by the hot object inside the cup will be the same amount of energy that will be absorbed by the liquid. Most of the time, it's just water that they are using, the liquid inside the cup. So when you mix two objects of different temperatures, heat flows from the object of higher temperature to an object of lower temperature until they reach what we call equilibrium. Equilibrium, class, means that there's already a sense of balance between the two materials. Doesn't mean that a process stopped, but rather doesn't mean that the process stopped, whatever that process may be, if you're going to reach higher professional subjects later. When you speak of equilibria, it has only something to do with the rate of the direction of anything. Let's say, for example, in this case, heat in this direction is the same in this direction. So the two, since they have the same rate, are said to be in equilibrium. It doesn't mean that when we speak in equilibrium, stop na siya. It stopped already or the process already stopped. No, it's just that the rate in which the transfers occur is the same. When they are already at the same temperature, they will reach what we call as equilibria. So during heat flow, the heat is lost from the hotter object and is gained by the colder object. Thus, the heat lost by the hotter object is also the heat gained by the colder object. The heat lost and gain are equal in magnitude but opposite in direction, and as such, the result is zero when added. So this is your calorimeter cup, and this is the common thing that is being used in the laboratory when the actual experiment is actually performed. Now, in my time class here, it's already 2:24, and I'd like to give you a break. So I will just pause the recording here. I'll give you a 15-minute break. I also have my break. I will just drink water. Then we come back after 15 minutes. You need not leave the Zoom, because if you leave, we cannot use the same link already. Anyway, your videos are already closed. Let's come back after 15 minutes. So that would be 30. That would be 2:40. Okay, 2:40, we go back here. You will know I'm just here when my video is already open, and I will continue with the discussion of the phase diagram. This is important, very important in the understanding of latent heat and sensible heat. Okay, class? I will stop sharing. So you are given a 15-minute break. So now my time is 2:25. We see each other again here by 2:40. Okay, 2:40. Okay? Okay, I'll close my video now. We'll resume at 2:40. Okay, so we'll go back to the part where we ended. Where is that? Let me just check last time. Share again. Okay. So I hope you are all awake there in the other end. Please bear with me. We can finish this one, but I need your full attention, because what I'm going to discuss is not as easy to follow as the rest, and it has sample problems, 2 sample problems at the end, and that would be it for the first module. So please bear with me. Now we go to the phase diagram. So in the phase diagram, or we call this also the heat curve, you have a picture representation or a graphical representation of the phase transitions that a particular material undergoes, and the corresponding temperature changes, of course, in the process that is needed before this particular material has to undergo phase transition. So there has to be a corresponding change in temperature first prior to a particular change in phase, if I may say. So what you have here is the temperature on the vertical axis, and you have here the amount of heat that is being required, or the amount of heat that a particular material has to absorb. That way it reaches a particular what we call state or phase. Let's say I will just talk about water as a very simple example. So water below 0 degrees Celsius, where it could be in the, where it is in the solid phase, is in what we call the supercooled state. The supercooled state, meaning -20, -25, or even -1, your water is in the supercooled state or supercooled solid state. Now, it needs to increase its temperature to 0 first before it can change phase. So this is the change of phase here, the red line, to the liquid phase. So from, let's say, -20, your water reaches 0 degrees Celsius and it's still solid at that particular temperature until and when there is energy that is supplied, heat is transferred to it. That way it changes phase. But notice that if this is the temperature axis class, it's a constant temperature process, whereas this one is an increase in the temperature. So from 0 degrees Celsius solid, it is now turned into 0 degrees Celsius liquid. Now your liquid water needs to further increase its temperature to 100 degrees Celsius for it to be able to convert it to water vapor. So from 0 degrees Celsius liquid to 100 degrees Celsius liquid. So there's an increase in the temperature but the same phase or state. Now once in the 100 degrees Celsius state or phase, water at constant temperature changes phase to water vapor. We call it steam or gas. So it requires energy for that. And in this process, the change of phase is constant temperature. But now you have a 100 degrees Celsius liquid converted to 100 degrees Celsius gas. So at this point, your water is already in the gas form. Now, since it's already in the gas form, you need to, let's say, for example, you want it to be reaching what we call as the superheated vapor form. So we need to increase its temperature further. That way we can refer to it as what we call as the superheated steam. Superheated steam or superheated water vapor. So why superheated? Because already your water here is in the vapor state at 100 degrees Celsius. You increase further its temperature, it would still be remaining as vapor, but the state now is what we call as a superheated vapor or a superheated steam. Okay, so let me read what is written in the paragraph below this phase diagram. Now, the plateaus, the ones that are in red on the curve mark, are the phase changes. So the temperature remains constant during these phase transitions. The sloping line, you could see the green lines indicate a temperature change, specifically a temperature increase. So the phase of the substance in this case remains the same during this temperature transition. So it's called a temperature transition because there's a change in temperature, but the phase remains the same. Now, water is a liquid which has a high boiling point strongly because of the hydrogen bonds, strong hydrogen bonds between the water molecules. It is both a strong hydrogen bond donor and a strong hydrogen bond acceptor. So the first change of phase you see here is melting, in which the solid turns into liquid. So from super cold solid, it turns into liquid in the process of melting, in which the temperature stays the same while the water melts. The second change of phase is boiling as the temperature stays the same during the transition to gas. So this is, by the way, class, sorry, this is the melting, the turning of the solid to liquid, and this is the boiling, the turning of the liquid into gas. So both, since they are red lines in here, are phase transitions, a change in phase, in this case here from solid to liquid, in here from liquid to vapor or gas. But before this phase transition has to occur, your substance, in this case water, needs to be reaching a certain temperature for it to be able to change its phase. Otherwise, it cannot change phase directly. What I mean is, hindi pwede nga from liquid, madiretso lang siya dayon sa gas without it increasing its temperature first to a particular temperature. That way, it's ready to be transitioned from liquid to gas. So there is no direct thing like that. Unless we have what we call, in the case of a special case of sublimation, wherein there's a direct change from solid to gas without having to pass through the liquid state or phase. Now, let me go to the sample problem. So I have two in this particular module. So the first sample problem talks about aluminum. Okay, a 175-gram hot aluminum, the temperature of which is 100 degrees Celsius, is dropped into an insulated cup that contains 40 ml of ice-cold water at 0 degrees Celsius. If the specific heat capacity of aluminum, the CP of aluminum, is 0.90 joule per gram degree Celsius, what is the final temperature of the mixture, referring to the mixture of the aluminum and the ice-cold water where it was dropped into in an insulated cup? So the first thing we do when whatever we solve class in engineering, whatever you solve, you always start with the given, especially if it's a worded problem. Unless otherwise it's in the form of an equation. But if it's the word problem, it's really very important that you write the given information and the required information, because these two already tells of a picture of how much you understood of what the problem is talking about. If the given information is already erroneously represented, meaning sala na, then the one who's going to read your solution will already have an idea that in the first place, you do not understand the given and the required. So how will that person expect that the answer will be correct when in the first place, the way the given is presented is already wrong? So in this case, we group the given information. So for aluminum, these are the given information. The mass is 175 grams. The initial temperature is 100 degrees Celsius. And the specific heat is 0.90 joule per gram degree Celsius. I think everybody can follow this one. We got that from the first statement here. Until this part. Now, this hot aluminum is dropped into an insulated cup which contains ice-cold water. Ice-cold water because its temperature is already 0 degrees Celsius, and you are given the volume of that ice-cold water, which is 40 ml. So you group your information in this manner. That way, when you substitute later values, it would be easy for you to pick up the information because you have already grouped them as they should be grouped. Okay, so the required information is what is the final temperature of the mixture, meaning what is the final temperature of the water with the aluminum, the hot aluminum on it already when you dropped it. Now take note, class, that it's talking about the final temperature, meaning it will be at a point when your aluminum and your ice-cold water is already equilibrated, meaning the temperature is not expected anymore to change. In this case, I will underline that. So final temperature. Now, you have to remember that the final temperature that we're talking about here, since your aluminum is dropped in the ice-cold water, will be the equilibrated temperature. And as such, at that condition, the temperature of the water, ice-cold water, and that of the aluminum has to be equal. So the final temperature of the aluminum and the final temperature of the water has to be equal because in the first place, they are already in what we call a state of equilibrium. So that's why the problem really used the term final. So what do we do? So if you recall our discussion a while ago, whenever there's a transfer of energy in here in calorimetry, when we talk about calorimetry, here in calorimetry, we have this. Q lost by 1 plus Q gain of the other should be equal to 0 if the materials we're talking about is in one environment. And since your aluminum and your ice-cold water is inside the insulated cup, then we can say that these two are in the same environment. So Q lost plus Q gain should be equal to 0. Or shall we say the amount of energy that aluminum released because it's hotter than the ice-cold water is the same amount of energy that was absorbed by water. Coming from this particular equation that Q lost plus Q gained is equal to 0. So the substance that lost heat is aluminum. The substance that gained heat is your water. So the MCP delta T of aluminum plus the MCP delta T of water then has to be equal to 0. From the table on top, I will not go back to it. The CP of water, because it was presented already, the CP of water class is 4.186 joule per gram degree Celsius. And then the water, the unit here of the water or the amount of the water that is given is in ml. And since our formula here is mass, there's a need for us to convert the volume here. So there's a need for this volume to be converted to mass. And for the volume to be converted to mass, you need to use the density of water. Density of water is 1 gram per ml. So if this 40 ml is multiplied to 1 gram per ml, it will give you the mass of the water, which is already 40 grams. So 40 ml times 1 gram per ml, that gives you the mass of water, which is 40 grams. Okay? So with the mass of the water, which is 40 grams, now you are ready to substitute in the formula that we have, the original formula that we have. Mass of, let me get rid of this, mass of your aluminum, which is 175. That's not 75 glass. This is 175. And then you multiply it with the CP of the aluminum, which is 0.9 times the change in the temperature of the aluminum. So its final temperature minus its initial temperature, which is given at 100 degrees Celsius. We don't know what is that final temperature. It's the thing that we're looking for. And this final temperature of the aluminum is the same final temperature of your liquid water. So for the water, you have now the mass, which is 40 grams coming from here. And we have the CP of water from the table on top, which is 4.186 joule per gram degree Celsius. You make use of the CP of liquid water. You multiply it with the difference in the temperature of water, final minus initial. It's stated in the problem that the initial temperature of ice-cold water is 0. The sum of these two is to be equated to 0. Giving you a final temperature of 28.73 degrees Celsius. So meaning, when the aluminum and the ice-cold water already reach a state of equilibrium, this will be the temperature that will be measured by your thermometer later on when it's dipped into the water inside your insulated cup. That would be 28.73 degrees Celsius. So there's an error here, class. This should be 175. So I missed writing the 1. So 175. But the final temperature is 28.73 degrees Celsius. Okay, any question? Any question, class? Okay, none. So we will proceed. So what is the amount of heat required to convert, this time for number 2, 100 grams of ice? Take note, at -5 degrees Celsius. So this is subcooled solid. Your ice is subcooled solid in this case because -5 degrees Celsius. To steam, this is water vapor at 120 degrees Celsius. So if I will annotate, oh, wait class, I cannot, you will be able to see. I will lower it down. Let me check. Wait class. Okay. This one here, your ice here is subcooled solid. In here, your steam is said to be superheated vapor or superheated steam. So what would be the corresponding amount of heat required to convert from a subcooled solid at -5 degrees Celsius to a superheated vapor at 120 degrees Celsius for this much of water? 100 grams. Okay, so if we will proceed here, let me just not any for now erase. So you need heat. So your given is that you have a mass of water of 100 grams, and your required is heat to convert ice at -5 degrees Celsius to steam at 120 degrees Celsius. So what is the total amount of heat needed? So Q total. You need then to write the phase diagram. So your phase diagram, I'll erase now this one so we can go up. Oh, wait, there's a question. Miss, I have a question in problem. How did we able to come up with the 28.73 degrees Celsius? Okay. How did you come up with the 28.7 degrees Celsius? Okay, let me just do the calculation. I'll show it to you. Let me just get my calculator. Wait. Okay. Oh, so you have to multiply 175 to 0.9. That would give you 157 here. So you will have 157.5. It is to be multiplied to T. I'll just write it as T minus 100. On the second term, you will multiply 40 to 4.186. So that should give you 167.44. And this should be multiplied to T minus 0. And this is equated to 0. I'm coming from here, okay, from this part here. So a T minus 0 is a T. So I will combine these two. So you have 157.5 plus 167.44. So you have a total of 324.94 T. And this one, this 157.5 times 100 is negative. So if you transferred it here, if you transfer it here on the right side, that would be positive. So 157.5 times 100. So that would be your 15750. So the T will be 15750 divided by 324.94. That would be 48.47. Okay, let me check. So probably the error here is in the 75 because it's supposed to be, let me check on Tab Class, it's supposed to be 175. So this should be 175. 175 times 0.9. So that would be 157.5. Let's say I will use only the 75 times 0.9. That would be 67.5 plus 167.44. I use that as a divisor. And I will multiply it to 75 times 0.9. Okay. So the answer would be 28.73 if it's only 75 grams that is placed in here. But since the problem says that it's 175, so if it's 175 class, the temperature, the final temperature is 148.47, okay, degrees Fahrenheit. If we stick to what is stated in the problem as 175. Okay? Okay, somebody wrote on the chat box. Please, the answer should be 48.47. Right. Because class, the answer that I place in here is for the 75 grams. It should have been 175. Okay? So the answer, which is 28.73, is actually just for the 75 grams. So that you won't have to do anything there in your computation, then make the 175 here in the given to 75, or else you change the answer. So this is the solution. I know how you know how to do your algebra. Okay. Thank you for bringing that up, Miss. This is Miss Marianne. Okay. Sige. So the 28.73 actually class is for the 75 that I used as given, not based on the problem. It's maybe in a hurry to place in here the solution. Okay. Some more questions before I go to number 2.
No, miss.
Okay, I'll clear the markings. Thank you, ladies, for that. It happens. Okay, especially if we're in a hurry to prepare this ahead. Unlike in the times before that we just go to class, bring our whiteboard, and that's it. We know already what to talk about. But when we have to prepare everything in advance to be written here, especially in the process of typing, there will be a lot of typo error. Anyway, so in the process of changing a subcold solid water at -5 degrees Celsius to a superheated water vapor at 120 degrees Celsius, this will be your corresponding phase diagram. And you are required for the total amount of heat. So we start with the -5 and we increase the temperature to 0. So from super cold solid to liquid solid still. This is still solid. Super cold solid at -5 degrees Celsius to 0 degrees Celsius solid. Then you have a change of phase here. Solid water to liquid water still at 0 degrees Celsius. Then from liquid water at 0 degrees Celsius, we need to increase its temperature. So there will be amount of heat needed here to 100 degrees Celsius. So this is liquid water at 0 degrees Celsius and liquid water at 100 degrees Celsius. Before it's turned to steam at 120, it needs to be turned to steam at 100 degrees Celsius. So there is corresponding phase change here at constant temperature of 100 degrees Celsius. So 100 degrees Celsius liquid to 100 degrees Celsius vapor. Once in the vapor already, then it's ready now to increase the temperature to 120 degrees superheated water vapor or superheated steam. So this will be the complete phase diagram for this particular problem. So we will need to account for the sensible heats. So the sensible heats will be represented by these green lines, where temperatures needs to be elevated or increased. And we also need to account the latent heats for the change of phase or for the phase transitions. So for the first sensible heat, this one, you have MCP delta T. The CP that you will use here is the CP for ice, which is 0.5 calories per gram degree Celsius. The mass is 100 grams. And this is your temperature change. Final temperature is 0. Initial temperature is -5. Your Q1 is 250 calories. Okay? Then we have the phase transition from solid to liquid. So latent heat of fusion. So we have 100 grams of water and we use the heat of fusion of water, which was shown to you a while ago, 80 calories per gram. Here it is. 80 calories per gram. Your solid turns to liquid. Okay, so we go back and we just multiply it to 100 grams. So for the, look at this, for the change of phase from solid to liquid, this much of energy is needed. So 54,000 calories compared to this one. Then once it's already in the liquid phase, you need another set of energy, the sensible heat, to convert it from liquid to steam. So in this case, you'll be using, by the way, class, this should be sensible heat for, this is not class steam. Okay, I'm sorry. Okay, I'll annotate here. Since this one, your Q5, you have here sensible heat Q3, latent heat, where am I? Wait, class, ha? I got lost. Naglumpat ko, goro. Tingala ko nga nakibot ko. Here we are. So we have here the sensible heat for solid. We have here the latent heat for solid to liquid. We have the sensible heat here for liquid. So as such, we use the CP of water. Okay? I thought I made a mistake again. So the CP of water multiplied to 100 times the change in temperature. So from 0 degrees Celsius water to 100 degrees Celsius liquid water. So in here, you have a Q3 value of 10,000 calories. This one is just 8,000 calories. Naglumpat ko gali sa evaporation. When we have now the latent heat of liquid water turned to steam at constant temperature, this is the highest amount of energy in the entire phase change. So you have 54,000 calories because we have 100 grams of water multiplied to the latent heat of evaporation of water, liquid to gas. It's here. Sorry class, ha? Naglingin ng oras sa ako, mouse. Hindi na siya. Here, so you have 540. Okay, you have 540 here. Liquid to gas. So we go back there. So latent heat, you have 54,000 calories. Then it's already gas in here. So we have the last energy, which is the sensible heat to increase the temperature of water vapor to 120. So in here, you need the CP of the steam. So 0.498 for the CP of the steam, the same mass. And the temperature change is from 120 to, or from 100 rather, to 120. So this is the amount of energy needed. For the total required energy, that way from -5 degrees Celsius, supercooled solid, you will have a superheated water vapor at 120 degrees Celsius. This is the amount of energy. So you just have to add up Q1, Q2, Q3, Q4, and Q5. And this will be the total amount of energy required. Okay? Now, here is the downloadable version of what this was discussed to you for the entire module if you want to download it and have it printed. Okay? Now, any question?
Miss, need pa to namon i-drawing ang graph to, Miss. Magamo ni Miss. Aramis.
Hindi siya. If you're
Miss.
asking me, it's better you write it this way. That way, you'll be able to account properly all the cues that you need to account because it's very clear here. You start with supercooled, then you have phase transition, then you have liquid to vapor, then you have another phase transition, and then you have vapor to superheated vapor. It's better because you get to see the phases, the phase change and the corresponding change in the temperatures as well. Though maklear gid sa imo ang path in which your water has to go through. Okay? You get it? But if you think this is difficult already, then you may opt not to anyway not present it. But I'd rather have this presented by you para clear ang imo nga path. Okay?
Thank you, Miss.
Sige. Who else has a question? Any question?
Mute ka, Miss.
Excuse me, miss. Naka-mute ka, miss.
Okay. I'm reading actually what is written on the chat box. What if there was no mass given? The answer, okay. What if there's a mass given? There is no mass given. There should be a mass given. If there's none, then that would be per unit mass. Your answer would be per unit mass of the substance. But that's a very good question. If there is no mass given, then your answer should be per unit mass of that substance. That way, if a corresponding amount is given already, all you have to do is multiply your answer. Okay?
Okay, miss. Thank you.
It's okay. You're welcome. Some more questions? Okay, so if there are no more questions, I'll stop sharing here because I will change to our, like to go back to our, by the way, the modules. I need to present to you the things that, wait class ha, arrow, back arrow. Okay. In here, in this module, you need to submit your first assignment. Do you see the page that I'm working on? Do you see the page that I'm on?
Yes, miss.
Okay, it's August 26 class. It's written here, August 26. It's because I placed also in our announcement. I'll go back to that so I can present it in class. I will now stop recording. Wait.